Well, in the last session, we were talking about digital signatures, and we had a problem. The problem was that I had a big file, let's say 1 gigabyte, and with my naive method, the signature occupied the same as the file. So I would like to have some primitive that helps me reducing this size. And this is going to be the main motivation to describe a new cryptographic primitive. Okay, just to make a quick summary of what we were talking. We were discussing the digital signature. We find in the last session how to generate these signatures. Essentially, each user is using his or her private key. And then we had the problem of big files. Okay, and the solution was to split our big file into small chunks and then use our symmetric encryption algorithm using our secret key over each of these chunks. The problem, as I said, is that we end having a big signature, in this case as big as the message. So we said that we wanted something to fix this problem. And this is where we start. So, and the cryptographic tool that is going to help us, which is a really useful cryptographic tool, in fact, is going to be the hash functions. And this is going to be the third cryptographic primitive that we're going to see. And yeah, let's discuss the what is a hash function using a simple example, okay? And not the digital signature. Later we will apply the concept of the hash function to the digital signature, but before, let's start with a simpler with the simplest use case, okay, which is a database search. Okay, let's consider that we want to search a record in a database, okay, and the records contain postal addresses. Okay, let's say, and they are made of characters like, I don't know, Spain, Barcelona, Badajoz, 73, all these, in fact, all these postal addresses are addresses of UPC, my university. So, well, in general, I have a database with a lot of registries, and each registry contains a postal address made of characters. I want to consider the problem in which I have to search an address in this database of postal addresses. So, let's see one naive way of doing this. The idea is we alphabetically order these addresses in the database, and then if we want to search, and then we want to search for an address. Let's say that someone provides us an address, and then I want to search if this address is in the database. Then one naive way of doing this is search character by character. So if this is the address that I'm provided, then I go to the database. The registries in the database will be sorted alphabetically too, and then I go character by character comparing this each character. So if I find an S, okay, there are a lot of registries with S, then I go and see if there is a P and so on. So character by character, I compare until I arrive at a point in which either I find the address or either I don't find it, okay? But this algorithm, in fact, has a terrible performance because, you know, a lot of addresses are going to have like the same beginning, and doing the match character by character is really a bad way of doing this, okay? We are going to see an alternative implementation for this simple use case using a hash function, and the example will illustrate how the hash functions work too. So let's try to design, let's say, a dummy hash function, okay? A simple and dummy that hash function. In this case, what I'm going to, the hash function, to design this hash function or to implement this hash function, what I'm going to do is to use a table. And each character that may appear in the address, we're going to translate each character into a value. For example, character 0, because we have postal addresses, so I may have the number 30 in the postal address. Well, the character 0 is going to have an equivalent value, let's say 0. Let's put it simple, and for the numerical characters, I'm going to assign the same numerical value, okay? But, you know, things get more interesting when I have a character that is not a value. Then let's say that, for example, for character A, I'm going to assign the value 10 and so on. So I create a table. For this dummy design of my hash function, I create a table in which for each possible character that may appear in a postal address, I assign a value, decimal value in this case. Okay, and now how do I perform the dummy hash in this case? Well, then I sum all the values of the characters and, for example, make modulo 100. So, for example, if I have an address, I don't know, Spain, whatever, I take the first character, go to the table, see which is this value, I don't know, for example, let's say 13 or whatever, I don't know, or 23, and then I add I go character by character, and then sum all the values, okay, and then I obtain a value, the total sum, let's say 954 is the value. But then I do a modulo operation, which means I just divide this number by 100 and take the remainder, in this case 54. And then I say that 54 is the hash value of the address. As you see, the hash is mapping an input of variable size, because addresses can have different sizes. And I take any possible value of different sizes, and then the hash outputs one single value which has limited size. In this case, the output size is two decimal digits. So my hash function is taking strings and outputs a two decimal digit value. And then the idea is that I will sort my database by this hash number. And then I will search by hash instead of searching character by character. Let's see this in this example. So now each string has an associated hash value, okay, which is of fixed size. In this case, two decimal digits. So now when I want to check if an address is in the database, I just take each character with my table, I sum all the values, and then I take the last two digits of this sum, and this is my hash. And then I go. Now my registries are ordered by hash, so I just, if for example the address gives the number 18, I go to the database of registries and say, well, no, this address is not here because this hash is not here. Well, but if for example the hash gives 17, then I should go to the database and try to see if there is an address there. Okay, but you probably are wondering, any problem with this simple idea? Well, yes, we have a problem here that is obvious. That is the following. I mean, what happens if two different addresses have the same hash, for example 54, so then, well, this is what we call a collision in a hash function. These are two different inputs in the hash function that provide the same output, 54 in this case. And these two different inputs are called a collision. Well, in my example, well, this may happen, obviously. Okay, so well, let's see this in a picture. Okay, and yeah, define the concept of collision. Collisions are different inputs that have the same output in a hash function, as I said. Okay, and this is always, I mean, in a hash function, always there are always collisions, always exist collisions. Why? Well, because the input can be of any size. So we have infinitely many inputs here, and the hash function always provides a fixed output. So there are infinitely many different inputs that go to the same output. Okay, so collisions are always possible in a hash function. Okay, in our example, we could solve this idea by, okay, I may have two different addresses on the same hash. Okay, well then, but still is useful to use a hash function like the one that I described, because what I will do is take the address, compute the hash, and then I have here a collision. Well, it means that in this hash value, I have to store two addresses. But now the search, and now I can do a alphabetic search and then try to find the address. Probably I'm going to go faster here because I have less registries to compare with. Okay, so, but still you may see that collisions are a problem. Okay, because it turns my algorithm again in something slow, because if there is a collision, then I have to look inside these two addresses to again find out if the address that I'm searching for is here or not. Okay, so it is clear that it will be interesting to decrease the probability of collision. I mean, collisions are, by definition of the hash function, collisions are always there. I mean, always there is a probability of collision, but can I decrease this probability? And how can I do it? Okay, well, let's see some solutions for that. Maybe you can think in some solution, but I have a couple of solutions for this. Obviously, you might be thinking, okay, instead of taking 2 digits, why don't we take 4 digits, for example? This will decrease the probability. Okay, instead of it will decrease the probability by 100 more or less. Okay, so if we increase the modulo operation and take 4 digits, essentially I'm increasing the output possibilities. I am increasing the size of the output. So this is one solution: increase the size of the output, and this will decrease the collision probability. But it is not only this. I mean, a good hash function has to have enough size in the output. Okay, but the other thing is that it must assign different inputs, like to each of the possible outputs, more or less in a random way. Okay, or at least as randomly as possible. Okay, we call this pseudo randomly. So probably it's better to use, I mean, I can also build a new hash function and with a bigger size, let's say 4 bits in the output, 4 digits, sorry, decimal digits in the output, And I'm going to use an alternative way of building this, just to make sure that I assign things maybe in a more random way. The other possibility is to, why don't we take another table? Okay, so let me take some space here. Okay, so yeah, let's say that I want a hash with 4-digit output, 4-digit decimal digit output. Okay, I can do the modulo 10,000. This is a possibility, but to provide a better mixing between inputs and outputs, an alternative way could be generate another table. Okay, in my first table, then the character 0 went to value 0. This was character, this is digit. 1 went to 1, A went to 10, and so on. Well, in this case, I can have another table different in which 0, I don't know, goes to value 13. I don't know. 1 goes to value 21, and so on. Okay, it's a different codification for each character. Each character goes to a different value. And then my hash is simply, I take the letters of the address, use this codification table, then do a modulo 100, and I obtain 2 digits, let's say 54, and then I do the same using this other table with is another codification, and then do sum, do modulo 100, and then I obtain another 2 numbers, I don't know, 73 for example, and then the hash is 5473, for example. Okay, the idea is that the input goes like in a random way. The output of the hash function is assigned as randomly as possible. In fact, in real hash functions, what we do is to make this process very, very closely seem like we are assigning a random number to each input. Okay. So, yeah, but this is the concepts that we describe are just for a dummy hash function, but real hash functions used in cryptography are just one-way hash functions in which collisions, we want that collisions are the probability of a collision is virtually impossible or computationally impossible. It is impossible in practice that there is a collision. Okay, this is the type of functions that we use in cryptography. Functions in which it is impossible it is impossible that a collision happens. In fact, if a collision happens, this means that the hash function is not useful anymore and it must be deprecated because it is broken. In fact, this has happened with, for example, SHA-1. Some people find a collision in a SHA-1 hash function, which was one of the most used hash functions in the past for some years, and now is deprecated because someone find a collision. Okay, so what do we need to create a hash function in which collisions are virtually impossible? To achieve this, I need a cryptographic hash function, and the first thing that I need is a huge output space. Okay, the output space is not 10,000 or something like that. It's incredibly huge. Okay, for example, is a number, and hash functions, the output of hash functions, of real hash functions, is not expressed in in decimal digits. It's expressed in bits. So, and typical hash functions, for example, the most typically used now is SHA-256. So it's a hash function that takes a variable input and outputs just 256 bits. Okay, 256 zeros and ones. So this is a huge number. Okay, the possibility the output of a hash function goes from of a SHA-256 bits hash function goes from 0 to 256 minus 1 is this number. Okay, and this number is huge. Okay, this is on one side, and on the other side, to achieve a cryptographically secure one hash function, and it must behave as a random oracle. This means that we must take an input, and the function behaves like associating a random value of 256 bits. Okay, in cryptography we call this a random oracle, because I ask the function to assign a random value. Okay, it's like an oracle because it's answer me, and I go here and I provide an input to the hash function, and the hash function provides me a random number of 256 bits in the case of the SHA-256. If I achieve these two properties, then I will have a hash function that is virtually free of collisions, and also that it is one way. It means it can be computed in one way, but not in the other way. And let's see this in more detail in the next slide. The first idea is, okay, we're talking about a number of 2 to the power of 256 minus 1. I mean, this number is big, but how big? I mean, well, more or less we are talking about the number of atoms of known or observable universe. Okay, so the random function is like you provide an input, and it is assigning an atom randomly to this input. Okay, so it's huge. The total number of possibilities with 256 bits, we have a huge number. Okay, and the other idea is that we are assigning this randomly. If I assign, it's like assigning randomly. If the function is like assigning random, it means that if I give you the output of a hash function, I mean, there is no way to go back to anything that, I mean, there are no equations to go from this value to the input, because essentially the process of assigning a hash value is like assigning something random. In other words, it means that it cannot be inverted. I mean, provided an input is not a, I mean, in fact, it's not something, the assignment is not random. It follows some operations, some well-known operations, okay? All the description of how to obtain from an input the output of a hash, this is very well documented, okay? It's perfectly specified, okay? But the behavior is like assigning randomly. It means essentially that we do a lot of operations that can be done in this size, but we cannot find equations to go to the other side, okay? From one hash, it is not possible to find anything that when you hash it, you obtain this value, okay? Other than, I mean, the only way that you have is this way. I mean, provided an input, you apply the hash function and you obtain the hash. Sometimes the input is also called the pre-image, and then the hash is also called the image. So provided an input or a pre-image, is easy to compute the hash or the image. So this way is easy or doable. But the other way around is not doable, because the operations that we do here are highly they are non-linear operations, and they are really impossible to invert. Okay, so this is why we say that hash functions in cryptography are one-way hash function. They can be computed in one way, but not in the reverse way. And the only way, I mean, and then if I give you a hash, then the only way that you can check if this hash is of something that you, I mean, the only way to reverse this operation is to try some input here. I mean, maybe, the only way is to try an input, hash it, and see what it outputs, and check if outputs the thing that I want. Okay, so this is the only way to break a hash function. The problem of this method is that if you try randomly, then you are trying to guess like an atom. So the number of tries that you have to do is of this size. Okay, unless you know where to try. If you try random inputs to try to find something that gives a concrete hash, then you essentially need to do this number of operations. And this number of operations is of the size of the atoms of the universe, so it is outside of the scope of any computer. It is even out of the scope of the human scale, let's say. So essentially, the hash function cannot be inverted. And this also means that on one hand, we want a couple of properties from a hash function. First, it cannot be inverted, and second, we cannot find any collision. Okay, so if I provide you some input and you compute its hash, it is computationally impossible to find another different input that produces the same hash. We know that there exists infinitely many inputs that provide the same hash, but the problem is to find it. I have to do a number of operations that is outside of the scope. I mean, it's not possible. If I try to do operations, the probability that I find something the probability that I find a hash that is the one that I want is like finding randomly guessing an atom. I select an atom in the universe and you try and randomly guess it. Okay, so this is out of the scope of what a computer can do. Okay, so these are like hash functions. Okay, so just a summary then. A hash function takes an input of any size. You can put here 1 GB or the size that you want. Then we apply the hash function and we obtain an output. And this output is assigned to the input like randomly. It means that we don't if I have the output, I don't have equations to go here. This is not possible. So the only way that I can try to find something with the same hash is try inputs. But the problem is the number of tries that I have to do is huge to find a collision. And yeah, this is the idea. And then this is why we call it one-way hash function. Okay. Here we say that in a space of 2 to the power of 256. Okay. And again, this is something that we did in the last lesson too. So if I have a good hash function, then if I change one bit here in the input, if I have a 1 GB file, for example, with a movie, and then I take this and just change 10 for one in all these gigabyte, then the hash function, how many bits in the output should change? Well, again, 50% at random positions, because this is like if I change a 0, this is a different input, and for a different input I assign a totally randomly selected output. Okay, and you will see this behavior in practical cryptographic hash functions. So then the idea is that for each input that I provide to the hash function, Then I do a hash and I obtain a value, in this case of 256 bits. Here, these 256 bits is expressed in hexadecimal characters. It means an hexadecimal character goes from 0 to 9 and then 6 letters, A, B, C until F. So these are 16 possibilities, and which means 4 bits. Okay, each hexadecimal character of here has 4 bits. So I have 256 times divided by 4 number of hexadecimal characters. So, well, this is a way of expressing the output of the SHA-256, and you will see also this something similar here in addresses in blockchain, because in blockchain the account addresses are hash values of public keys. In many systems like Bitcoin, Ethereum, and so on, an account is a hash function of a public key. And we already know what is a public key. And now we know what is a hash function. Many of them just the first, and in fact the hash that they use is SHA-256, and they just, for the account, we just take the 161st bits. So you will see this divided by 4. In Ethereum, for example, you will see 40 hexadecimal characters. And this is an address in Ethereum, for example. Just to link a little bit this lesson of hashes with blockchain. So, going back to this picture here, if I take any input that I want, just a bit 0 or just a bit 1 or a movie or a song or whatever, and I hash it, I will obtain like 256 bits, which is like an atom. It's like selecting an atom, and it is impossible in practice to find anything else that goes to the same value. This means that, and this is very important, because the hash of some input data, can be used as a cryptographic summary or cryptographic digest of this input. So the hash of something is like a summary, cryptographic summary of this input, and is a perfect cryptographic representative of the input, because it is not going to be anything else in the world that will have or will give the same hash. Sometimes we call this the fingerprint, because it happens the same with human beings. I mean, our fingerprint is something that, I mean, there are no two human beings with the same fingerprint. So we are bigger than much bigger than the fingerprint, but the fingerprint is enough to individualize, or it can be used as a summary of ourselves. I mean, it perfectly identifies us. Okay, and it is much smaller than us. So the same idea can be used here with hash functions. The hash of something is the fingerprint of the cryptographic summary of this thing. Okay, so now that we know the concept of hash functions, we know that they are one way because they assign outputs randomly, so we don't have equations to go back. The only way to break a hash function is to try different inputs and try to guess the output, but the output is huge, so it's really difficult to guess the output. And we know also that we can use it as a fingerprint or cryptographic summary. Then let's see some algorithms. Okay, and hash functions. Well, we have had many different hash algorithms during during the time. Okay, for example, MD5 or SHA-1 and so on. Some of them are broken. In fact, these two are considered broken. And today the most usedly ones are SHA-2 of the SHA-2 family, and the most widely used is SHA-256. this is used for many purposes, because the hash cryptographic primitive is, in fact, if I have to say which is, I mean, now we know symmetric cryptography, we know asymmetric cryptography, and we know hash functions. If you ask me which is the most important, clearly the hash functions are the most important, because they are the primitive that allows us to build more things. Okay, so they are really used, and this one SHA-256 of the SHA-2 family is the most widely used today. In fact, it is used for mining cryptocurrencies with the proof of work algorithm that you will see in other lessons. In fact, there is another family of hash functions which is called SHA-3 family, and in the SHA-3 family there is another algorithm that also outputs 256 bits, which is called Keccak 256. And well, this hash is also very well. It is mostly used in Ethereum. Okay, so for different purposes. For mining, we use SHA-2. The SHA-200, and if you see SHA-256, this belongs to the SHA-2 family, and in the SHA-3 family you will see also hash functions which is called Keccak that also outputs 256 bits, and this is mostly used in Ethereum, as I said. Okay, so yeah, to finish, let's apply this idea to our problem, and let's see how this can help in the digital signature. Maybe before we can, for example, use the hash function for another purpose. Let's use it first for another purpose. Let's say that we were saying that we had A and B, and let's consider that they want to exchange some information in a confidential way, and they are using a symmetric encryption. Okay, so they have to put the same key here and the same key here. Okay, and this key is of 256 bits, for example. Okay, so how can they share this key? Well, they can meet together one day, okay, and try to, and both of them will write in a paper the key, okay, and then when they are away, they use the same key. Okay, the problem is how they write the key in these papers, okay, with zeros and ones. So both need to write the same key with the 256 zeros and ones. This is going to be difficult and prone to errors. Maybe you could think, okay, for a human it is difficult to write zeros and ones. I mean, it is difficult to write 256 bits without making any mistake. So probably it's better to just use hexadecimal characters. Okay, for example, I don't know, A, 3, F, 2, and whatever. Okay, so in this case they have to write, instead of 256 bits, is divided by 4, so they just need to write 64 hexadecimal characters. Okay, but still writing down 64 characters for a human is very complicated. So the typical way of doing this is just to create some password, or some sentence. Let's say hello, I don't know, they agree one sentence with different words and with many possibilities, and then they hash this sentence, and then they use the output of the hash as share key. For example, this is one of the first uses of hash functions. Go from passwords or passphrases to keys. Okay, for example, this is one use. Another use is to apply this idea of the hash function to our problem of the digital signature. Okay, and then how we solve our problem of the digital signature. Well, the idea is that we had a movie, which was a file of 1 giga. And then what I do is create a cryptographic summary of this hash by applying a hash function. Okay, let's say a SHA-256. And then I obtain the summary, or the cryptographic summary, or the digest, or the fingerprint of the movie. Okay, and essentially then what I need to do is sign this summary instead of signing the movie. Okay, and for this example I'm using as asymmetric algorithm, I'm using RSA 2048. So, well, the hash is output is smaller, is 256 bits. Well, this is what in digital signature schemes you will see that you will have a hash algorithm to create the summary, and then a public key algorithm to sign this summary. The problem here is that, okay, I need to adapt, okay, because the output of the hash is not big enough, okay, and this is called what we call padding. Okay, I need to pad or fill in. I have to, use a pattern to arrive to this 2048 bits. That is what RSA needs, and this adaptation is what we call the padding. Okay, here this is not the real one. In the real SHA-256 RSA 248, well, there is another way of doing the padding, but this is the simplest approximation. But I can repeat 8 times the SHA, for example, and then I get my 2048. And then essentially what I do is just encrypt this 248 bits, and now my signature, encrypt this with my secret key, as always in the public key cryptography for generating a signature, and then my signature is only 2048 bits and not 1 gigabyte. Okay, and finally, to check the signature, essentially what I do is I receive the file being signed, digitally signed, and the signature. I need both now, and then what I do is if I want to verify that Alice provided a valid signature, what I need to put here is the public key of Alice over the signature, and it should output 8 times the hash. And then I take the film or the movie, and then I do a hash and obtain these bits, and I check that, okay, this is what I obtain is the hash, and it's repeated here 8 times. If these two match, then I say that the signature is okay. If this operation doesn't match, I say that the signature is incorrect, so it was not Alice who signed this. And with these concepts, we arrive to the end of this lesson, in which we quickly review the digital signatures. Then we explain the concept of a hash function, and we design a dummy hash function. My design is not useful in practice for cryptography because it's not collision resistant or pre-image resistant. Okay, but well, we discussed this. We discuss about collisions also. Okay, and then we talk about the real functions in cryptography, which are one way. They can only be computed in one way. Provided the input, you can compute the output. But if I give you the output, you cannot compute the input. Okay, other than trying, and this is computationally impossible that you guess some input. Okay. Then we discussed a little bit about hash algorithms and different families, about SHA-2 and SHA-3. And finally, we applied the concept of the hash function to a couple of things, just to derive a symmetric key from a password or a passphrase, and also for our problem of the digital signature verification. So this ends this lesson, and in the next lesson we are going to go further with hashes and discuss their use in several cryptographic parts of the blockchain. Thank you for all. See you next lesson.